now. But yeah, there's just these people finding ways to make GANs a lot more stable.
Very interesting. Yeah, and Dr. Liao put the name for that duality in the chat if you want to have a look.
Yeah, I think the constraint on Lipschitz constant is coming from this duality, but it's hard to explain in a very short way. Yeah, but I can kind of answer your second question, like why constraint of weights push the towards Lipschitz function. I mean, when you analyze the Lipschitz constants of the neural networks, you can do a recursive analysis by first analyze, for example, a linear layer. So convolution is one special case of linear layer. So if you do the analysis for the linear layer, that should be fine. And then you do it for the nonlinearity. So for ReLU is one Lipschitz. That's easily proved, can be easily proved. And then for TenH and other, you can do the proof similarly. So you can do this analysis recursive to show that if you constrain the weights to be in, I think they put in a cubic, right? Hypercube, right? It's from 0 minus k to k or something like that. It's, yeah, some constant k minus k to k. It's sort of like a hypercube. Yeah, you can do the analysis recursively to show that this bounded Lipschitz constants.
Okay, and would that affect what k the Lipschitz would have? Would this limit like that? Oh, I see.
Yeah, I mean the actual k value depends on the bound, the kind of the upper and the lower bound here, and also the Lipschitz constants of the nonlinearity used.
I see. Okay, very interesting. Okay, yeah.
Yeah, so one thing about the Earth mover distance, so for the high dimensional Earth mover distance, it's very hard to compute, as Michael said. So does the Wasserstein distance in the high dimensional case. That's why people use random projections to project your data from high dimension to very low dimension. For example, in the extreme case, it's one dimensional. And then you can do Earth mover distance efficiently in this one dimensional space. And then people prove that if your projection is random, then as your number of samples goes to infinity, you can still recover the Wasserstein distance. I think people already in the literature explore this idea. It's called a slice the Wasserstein distance.
So even if you go to 1D, if you have enough samples, then you're good. Wow.
Even if you go to 1D, but you go to 1D with different random projection at each time. And as this random projection number goes to infinity, you can prove some approximation accuracy results. Yeah. So this is actually used by quite a few papers in the literature. It's called a sliced Wasserstein distance. Let me try to search one and put it in the channel.
Is there a specific GAN network using that, like slice W GANs or something?
I think there are multiple papers doing that. I'm not sure exactly what paper, but yeah, it has been also used for other applications as well.
I found a paper that talks about sliced Wasserstein GANs, and also like they were using the same thing for like autoencoders. It's just slicing idea of projecting.
Yep, it's the same idea, just random projections applied to the high dimensional distance. Yeah.
So have W GANs totally rule out GANs? Like, is there scenarios where GANs are preferred over W GANs?
I mean, I think no one these days train GAN using the original GAN papers tactics. There are many advancements during the past few years, like spectral normalization. This is a must freak we want to train GAN efficiently, like share paper. This is proved to, I mean, it's shown to stabilize the training process significantly as well. Yeah, I didn't closely follow the literature of GAN, so I only know a few tricks. But if you want to make it like build a model match the state of the art, I think you need more trick. You need to learn more tricks.
So yeah, the instability is always an issue. Yeah. So this could be somehow similar to WGANs, right? Where they're trying to, they clamp the weights. Here they're doing some sort of normalization, I guess.
Yeah, I think they normalize the maximum singular value, which is the spectral radius of the matrix, weight matrix. Yeah, you can thought of it while also constrain the Lipschitz constant.
Nice. It's nice to see how they actually connect. Okay, that's it for me. If there are no more insights or questions from anyone. Okay, thanks a lot for listening, everyone. I certainly learned a lot. Thank you.
Yeah, one more thing you mentioned is about KL divergence. Oh yeah,
Yes.
Arsha has a question. Yeah, Arsha, go ahead.
Hello, can you hear me?
Yes.
Yeah. Well, one thing that I didn't figure it out actually was that WGANs was a solution for mood collapse when the variance of the things that the generator is generating is not that much, so that somehow it's just generating is somehow generating 1%, but with a little bit difference from the other one. If you notice, for example, for 1,000 times, we were actually having 1% with some very, very small details different from the other times. But I didn't understand that just based on for a discrete probability that WGANs will, W distance will give us the continuous measurement, we decide that this kind of this kind of divergence is going to be better for training GANs. I mean, the main idea just came from this slide. This is specifically a slide because the Earth mover, or because the Earth mover is continuous and the others are not.
Yes, but we also know that Jensen-Shannon does not have the problem that KL had, right? With the mode dropping. Right, because it's symmetric.
Yeah, I know. I mean, the main reason we choose the Earth mover is because it's continuous.
Because, well, it's multiple reasons. One is well, it's good, it's continuous. The other, I think, more important one is that you don't see the gradient vanishing issue that we saw with Jensen-Shannon in this case, because here, if like for this example, it's just a constant value for Jensen-Shannon, right? This is a very simplistic example, but still. So that the gradient here is 0, you have vanishing gradient, but here it's not 0, right? So that's another benefit that EM has over.
Yeah, does it have these benefits in comparison with TV as well?
Yes, if you look at TV again here, right? It's a constant value.
So yeah, just based on this difference, we have choose the EM.
Well, in this example, I see this, but I'm not sure why TV may not be a good choice for other.
Because TV naturally will penalize this mood collapse as well as EM. So I was wondering why not choosing TV, and I think that realized that maybe that's because of this continuity in the EM distance in comparison with TV.
So one question with respect to total variation is, can you actually efficiently compute it in the high dimension space? I thought you have in computing the TV distance, you need to solve a maximization problem yourself.
As
Oh,
far
yeah.
as I know, there is no easy way to compute
Yeah.
TV.
Yeah, that's why people didn't use it in practice, I think. And using Wasserstein distance, the nice thing is if you look at the duality, the Cantor-Robinson duality, and then you write in the form that
Yeah. It makes it easier to compute based on the
Yeah.
duality form, based on the dual form.
Exactly.
Thank you.
But one thing about the KL divergence, so you could go back to the color case or the bad case for the KL divergence, where you have a graphical illustration. No, the graphical illustration of the KL case.
Oh, so
No, the one going down all the way down. Yeah, this case.
oh, that's one. Oh, okay. So
Yeah.
here.
So yes, if you use kind of delta distribution, or you have discrete distribution, this thing will be like that. But one clever trick to combat this is to add noise to your data. For example, if I can add a Gaussian noise to the data, then I will have density, non-zero density everywhere, right?
So in the paper, they actually mentioned that a lot of other models add noise to combat this issue, but I think it mentioned that the output images were also blurry because of that.
You mean the generated output image becomes blurry, or?
I think they mentioned the final images that you get from the generator, yes, after training.
Okay, that I'm not so sure, but if you add Gaussian noise to your original image, it will be just
I see.
random scatter points to your image, and it will look very,
Quickly.
Yeah. Actually, this is the trick which is recently heavily used by score-based model, and we'll cover that in the maybe Lex or the Lex talk, where they add noise to the image and they annul the variance of the noise. By annulling, I mean in the beginning I add a lot of noise to the image. You can think of extreme case. If I add a lot of variance to the image, then the image contents will be disappearing, and the image becomes a noisy image, right? It's completely of noise. In that case, the density is just a Gaussian, bell-shaped density. And the KL divergence should be relatively easy to compute for that. And then I can gradually decrease my variance of the Gaussian noise. That is called annulling of the noise. And then by doing so, I'm still training my network. So I train my network at a different noise level and with different weights at each level. And the idea is, although KL divergence may be hard to compute at one level, especially the extreme level where I didn't add any noise, but it will become easier to, or well defined in the other noisy level. So it will be.
That makes sense. Yeah, I think a more advanced approach, like you mentioned, kind of fixes this issue that they mentioned here too, right? Because it says if you assume a Gaussian noise, then again, what I mentioned degrades the quality of the samples.
That's not generally true. I mean, with score matching, we'll see that actually adding noise makes the model better. And if you add the correct amount of noise, the model performs very well, even comparable with GANs.
I see. Okay.
Yeah.
So I think
actually,
they were aggressively promoting WGANs here, I guess.
No, I think because the training objective is different. When he wrote this paper, the score-based model is not becoming very popular to people. So people don't understand how good the score-based model can perform. But at this moment, score-based model and diffusion-based model performing well, and the key ingredients is adding noise.
Awesome. Thank you.
Yeah, sometimes we want to get rid of noise, but sometimes we want to inject noise into our data so that the learning becomes easier. Sounds very counterintuitive, but it works in the practice and also has a nice interpretation that we are learning in the future. Cool.